Good morning, calculus friends. So I want to continue with our exploration of related rates problems, and we were just about to do a ladder problem before we were rudely interrupted by that fire drill. So here is a ladder problem for us to work on right now. And so this is the classic ladder problem. And so the ladder is 17 inches or 17 feet, and it's leaning against a wall, so that at the base of the wall, the ladder is 8 feet from the wall. The ladder is sliding down the wall at 1.5 feet per second. How fast is it sliding out? So I'll give you a moment to write that down, and you can pause whenever you need to. And in a moment we'll do the problem. So the ladder problem, 17-foot ladder leaning against the wall, so the base of the ladder is 8 feet from the wall. The ladder is sliding down the wall at 1.5 feet per second. How fast is it sliding out? So I'll assume that you've paused and done whatever you need to do in order to write all this stuff down. JP, that includes you, so if you haven't written it down yet, please get out something to write with and something to write on and write it down. So we need to, first, I think it's useful to draw a diagram. So I'm going to draw a right triangle just like we did last time. And there's the ladder. And here's our right angle. So we know that the ladder is 17 feet. And we know that at the base, the ladder is 8 feet out from the wall. And if we do a little quick Pythagorean theorem, a squared plus b squared equals c squared, we recognize, hopefully this is another one of our favorite triangles. This is an 8, 15, 17 triangle. If you need to verify that that's the case, please take a moment to pause here and do a squared plus b squared equals c squared. You'll find that the missing side is 15. So we also know that the ladder is sliding down the wall at 1.5 feet per second. So I'm just going to make a little arrow here. 1.5 feet per second. So we know that it's sliding down. Now, as I talked about last time, the most important thing here for us to be able to do to even get started in these problems is to find a relationship. So, Jamie, I know this is a little bit difficult for you, but try your best to keep up with us finding a relationship. So let's get our relationship just like we had last time. So we have x squared plus y squared equals hypotenuse squared. And we know the hypotenuse in this case is 17, so we're just going to simplify that a little bit, and we'll jump up here and we'll have x squared plus y squared equals 17 squared, which is whatever that is, 17 squared. Hopefully I'll calculate that in a minute. And we need to go ahead and find the derivative, and remembering that everything changes with time, we will go ahead and calculate or figure out our derivative here. So taking the derivative of x squared, we're going to have 2x dx dt. And then doing the same thing for y, we're going to have 2y dy dt. And actually it didn't really matter what 17 squared was because the derivative of 17 squared is just 0. Now we're going to plug in all the stuff we can plug in and find the missing piece. So from back of the diagram, we know that the x value is 8, the y value is 15, and the dy dt is 1.5. So the x value is 8, so we got 2 times 8. We don't know dx dt, we'll solve for that in a minute. We know the y value is 15, and we know that it's sliding down the wall at 1.5 feet per second. Still equals 0. So we have 16 dx dt plus 45 equals 0. So we subtract 45, so we got 16 dx dt equals negative 45. Divide both sides by 16, and we get dx dt equals negative 45 over 16. And this is, the units here are feet per second. So negative 45 over 16 feet per second. And so there we have our final answer. That's how fast the ladder is sliding out from the wall when all of these conditions are the case. 8 feet out, 15 feet up, sliding down at 1.5 feet per second. So again, take a moment here to pause and write down all the stuff you need to write down, ask each other questions, ask Tina, she knows everything, she'll help you out, and we'll move on to the next problem. So here we are, the classic oil slick problem. JP, if you haven't written anything down, please make sure you're writing something down now. So here's the oil slick problem. We can imagine that some oil has been spilled into a lake or an ocean, such that we have a perfectly circular oil slick. The radius is increasing at a rate of 0.25 miles per day, which isn't really, it's a quarter mile per day, which I guess is probably a reasonably fast expansion of an oil slick. So find the rate of change of the area of the oil slick when the radius is 1.25 miles. So it's a pretty sizable oil slick. So again, it's going to be useful for us to find a relationship here between, or to connect all these quantities here. And so as we go back over this, we see that we have the radius of an oil slick, and we have the rate of change of the area of an oil slick. So something that is circular, that has an area and a radius, so the relationship that we need here clearly is going to be A equals pi r squared. That's our relationship. That's the most important thing for us to do. And we know that we want to find the rate of change of the area. So the rate of change of area is going to be dA dt. So we're going to find the derivative of this thing here using implicit differentiation and finding the derivative of everything with respect to t. So we do dA dt equals 2 pi r dr dt. And then all we need to do is fill in all the stuff that we know and find out the missing part. So we're missing the dA dt, that's what we're trying to find out. And we know that the rate of change of the radius is 0.25, that's dr dt. And we want to know the rate of change of the area when the radius itself is 1.25. So we'll just plug that stuff in here. So dA dt equals 2 times pi times the radius, which is 1.25, and dr dt is 0.25, and if I was smart, I'd have my calculator right here, right now. So I can do 2 times 0.25 is 0.5, and then 0.5 times 1.25 is 62.5, so equals 0.625 pi. That is dA dt, I think, anyway. 2 times 0.25 is 0.5, and 0.5 times 1.25, half of 125 is 62.5, so 0.625 pi. And then we can multiply by 3.14, and we have our final answer. Oh yeah, we need the units. So this is area, rate of change of area is going to be, in this case, cubic miles, come on now, M-I-L-E-S, cubed per day, D-A-Y. So there we have it, there's our final answer. So this is the classic oil slick problem. Again, pause anything you need to pause here so that you can get all the stuff down, all the words down, and all the work down. Pretty straightforward this one is. Kind of like Yoda there a little bit. Alright, so let's move on to a little slightly more challenging problem, but not much more. This is the melting snowball problem. These are all kind of classic problems that show up in pretty much every calculus textbook. So we have a perfectly spherical snowball, and it's melting. And the volume of the snowball is decreasing at a rate of 6 cubic inches per hour when the radius is 3 inches. So it's a good size snowball. Find the rate of decrease of the radius at that moment when the radius is 3 inches. So again, we need to find a relationship that connects all of this stuff here, the volume of a sphere and the radius. And so you probably don't remember this formula, but here it is anyway. Volume equals 4/3 pi r cubed. That's the volume of a sphere, 4/3 pi r cubed. So again, we're going to find the derivative of this using implicit differentiation. So we're going to do dv dt equals, bring the 3 down in front, so 3 times 4/3 pi r squared, and we can't forget the dr dt because that's part of the whole chain rule thing. And we can clean this up here a little bit. The 3 and the 4/3, or 3 times 4/3, that's going to cancel. So we're going to have 4 pi r squared dr dt, which I'm going to write up here. So dv dt equals 4 pi r squared dr dt. So back to the problem, we know that the volume is decreasing at a rate of 6 cubic inches per hour, and we want to know how fast is the radius changing when the radius itself is 3. So we need to plug in 6 for dv dt and 3 for the radius. So we'll plug those in right up here. So 6 for dv dt, 4 pi, and the radius is 3, so 3 squared we have right there, and we have dr dt. And of course 3 squared is 9, times 4 is 36, so we have 6 equals 36 pi dr dt. And then we divide both sides by 36 pi, and we get 6 over 36 pi equals dr dt. And then we reduce a little bit, and so we get 1 over 6 pi. And the units here are inches per hour, I think it is. Yep, inches per hour. So inches per hour. That's dr dt. That's the rate of change of the radius. And again, you would decimalize this, but I was a little dim and I forgot to bring my calculator up here. So anyway, so there it is. There's the final answer. So this is the classic melting snowball problem. And, so we have a melting snowball, which means the sphere is getting smaller, but this could just as well be a balloon, a spherical balloon that's being inflated. It's really just the same concept. Everything's the same. Still going to use the same formula, 4/3 pi r cubed. The volume will be changing. The radius will be changing. It's the same kind of problem, only instead of getting smaller, it's getting bigger. Instead of being a snowball, it's a balloon. It's all the same stuff. So we move on to another problem, which is also fairly straightforward, though I've saved the most difficult one for last, which we got one more to do after this one. So here's the expanding cube problem. So we have here that all edges of a cube are expanding at a rate of 5 inches per second. We want to know how fast is the volume of the cube changing when each edge measures 12 inches. So again, we find a relationship that connects all of this stuff together, the volume of a cube and the length of the edges, and I think that we should be able to figure out that the volume equals edge cubed, or side cubed, or whatever you want to call it, but I said edge in the problem, so I'm going to use edge. So again, we're going to find the derivative of this using implicit differentiation. So we have dv dt equals 3e squared dE dt. And again, what we're trying to find here is how fast is the volume of the cube changing. When the edge is 12 and we know that the rate of change of edges is 5 inches per second. So we're just going to plug those in. So we just got 12 and 5 to plug in. So equals 3 times 5 squared times, nope, that's 12 squared. The edge itself is 12, sorry, 12 squared, times 5, which is how fast the edge is increasing. So that's 3 times 12 squared times 5. So 3 times 5, of course, is 15, and 12 squared is 144, and so that's dV dt is going to be 15 times 144, whatever that happens to be. And the units are going to be, we're changing volume here, and this is in inches, so this is going to be cubic inches, because it's volume, per second. So we want to make sure we have the volume, or I'm sorry, the units in all of these all the time. So we got 15 times 144 cubic inches per second. That's dV dt. And so there it is, the expanding cube problem. I suppose we probably could have drawn a diagram for this, but I think it was all pretty clear without the diagram. So there it is. Again, pause whenever you need to pause. Write down all the stuff. That means you, JP, write this down, please. Jen and Mrs. Stirs, please make sure you're still paying attention. No giggling and laughing about, whatever it is you might be giggling and laughing about over there. So, on to the conical tank problem. This is the most difficult of the problems that we have to do today. So, let's get started. So, water is draining out of the bottom of a conical tank that measures 30 inches tall and whose radius is 10 inches. And we'll find out that this is actually important information in a few minutes. The water flows out at a rate of 6 pi cubic inches per minute. How fast is the height of the water decreasing when the radius is 4 inches? So we'll go over that again, and you should write all that stuff down so that you can have a reference point so you know what it is that the work is that you've just done and how it relates to the problem. So, water is draining out of the bottom of a conical tank. And basically, you should think about this as an ice cream cone. A cubic, or not cubic, a cone, not one of the pointy cones, one of the sugar cones, not the other kind of cone. And so it's upside down, so the point is down. Conical tank that measures 30 inches tall and whose radius is 10 inches. The water flows out at a rate of 6 pi cubic inches per minute. How fast is the height of the water decreasing when the radius is 4 inches? So as always, we start with a relationship, and I might as well start up here at the top of the page. So our relationship here that tells us about the volume of a cube is volume equals 1/3 pi r squared h. This is the volume of a cube. And pretty much anytime we have something that's pointy, 1/3 will be involved. So pi r squared h is really the volume of a cylinder, but basically a cube is just kind of a pointy cylinder, so it's 1/3 of the cylinder area or volume. So again, we're going to do some implicit differentiation here. But before we do that, we notice that we have two things here, actually three things that are changing. We have the volume that's changing because the water is draining out. We have the radius that's changing because as the water drains out, the radius gets smaller, and as the water drains out, the height gets less. So I am actually going to draw a diagram right now so that we can take a look at what that looks like. I think I'll put that at the bottom of the problem, and then we can discuss. So we have our little cone here, and we know that the cone is 30 inches tall, and the radius is 10 inches. I didn't really draw that very well to scale, but there it is, and the water is flowing out of the bottom of the cone. So we have the height, and that's 30, and the radius is 10. And so what we know is that there's a ratio of the height to the radius, and it's 30 to 10 or 3 to 1. So the height to the radius is 3 to 1, and that's important for us in this problem. And so I'm going to put that right here. The height to the radius is 3 to 1. And so when we go back to the problem, it's important here because we need to make a substitution. We need to either get rid of the r or get rid of the h so that we can only have two variables that we're working with here. So let's go back to the problem. And it says here that what we want is, we want to know how fast is the height of the water decreasing. So we want to keep the height in the problem. So we want to go back up here and we want to substitute away the r and change the r into h. So the way we're going to do that is we're going to do one of our little proportion tricks here, and we're just going to switch the r and the 3 because that's totally legal and legit to do that. So we have h over 3 equals r. So r equals h over 3. So what I'm going to do now is I'm just going to put the h over 3 in for the r. So we're going to rewrite the problem as v equals 1/3 pi times h over 3 squared times h. And we'll just do a little cleanup work on that. So h over 3 squared is really h squared over 9, and 9 times 3 over here is 27, and h squared times h is h cubed. So I'm going to write this as pi over 27 h cubed. That's our volume in terms of h only. So we're going to continue on here, and we're going to find the derivative of this implicitly. So we have dv dt equals 3 times pi over 27 times h squared times dh dt. And then we're just going to substitute in all the stuff that we know and do a little cleanup at the same time. So we know that dv dt, the volume, is how fast the water is flowing out, or the amount of water that's flowing out. So the water flows out at a rate of 6 pi cubic inches, that's the volume thing, per minute. So that's going to be 6 pi right here for dv dt, that's 6 pi, equals, and then 3 cancels with 27 to make a 9 in the denominator there, so it's going to be pi over 9. And h squared, so h is, well, what is h in this problem? Because all the problems we want to find out how fast something is changing at a certain moment. So in this case, when the h is, and so let's look back to the problem here and see what the h is supposed to be when we're doing this problem here. So whose radius is 10 inches. The water flows out at a rate of 6 pi cubic inches per minute. How fast is the height of the water decreasing when the radius is 4 inches? It doesn't actually really tell us what the height is at the moment that we want to find out all this information. But what it does tell us is that the radius is 4. But we know from up here that the radius is the height divided by 3. So if we know that the radius is 4, then we can bring that right up here. And we know the radius is 4, and 4 times 3 is going to make 12. So h is going to be 12 at the moment that the radius is 4. So we can plug in h is 12 right here. So it's going to be 12 squared. So times 12 squared times dh dt, which is what we're trying to find out. We don't know dh dt. So we can begin to solve for dh dt by multiplying by the reciprocal of this thing right here. So we're going to multiply by 9 over pi. So we're going to multiply that side by 9 over pi. So the pi's will cancel off, and I'll have 9 times 6, which is 54. So 54 equals 144 dh dt. And then we divide both sides by 144. So we got 54 over 144 equals dh dt. And I know that at least 3's go into these. So 3 times 18. So I got 18 over 3 into 144 goes 48. 18 over 48. I can reduce again by 6's. So I got 3 over 8. 3/8. So this is 3/8 of, we're doing DHDT, so that's inches. So 3/8 of an inch per minute. So our DHDT is 3/8 of an inch per minute. So going over all this again, we wrote our relationship here, which is volume equals 1/3 pi r squared. And we had another relationship here which was important, that the ratio of h to r, and this is always going to be the case when we have volumes of of cones, we always need to know this ratio of the height to the radius in order to finish the problem. And so we know that that's 3 to 1, and so we rearranged it so that the radius is h over 3. And we rewrote the problem here so that it was only in terms of h, because we needed h because that's what the problem was asking us to find, DHDT, so we need to write the whole problem in terms of h. So cleaning it up a little bit, we get v equals pi over 27h cubed. Do our implicit differentiation, dv dt equals all of this stuff right here. Clean it up and substitute in the stuff we need to substitute in, remembering that we didn't have h from the original problem, but we were able to calculate h when we went back up here because the r was 4 from the original problem. So we put that right in here, so we got 12 squared, and we did our calculations. Hopefully I did them correctly and reduced properly and so on and so forth. So we got 3/8 of an inch per minute. So there we have our lesson on related rates, and these are classic related rates problems, and these should be helpful to you in doing your assignment. Good luck.